All right, so let's see. I think it's a minute after. Should we get started? Z, you're gonna go first, correct?
Yes.
Okay, all right. So why don't I just go ahead, sorry.
I don't know if you have any introduction, before me, but
I was just gonna do a quick intro. We have several speakers tonight for you. We're really excited to put together this seminar. This is going to give a great overview on the newest SweRV cores that are open source. So our latest SweRV EH2 and EL2, which are part of the CHIPS Alliance GitHub. I'll put in the chat box the link if you want to go to the GitHub location for those, as you hear about them in the presentation. So Zvonimir and Robert from Western Digital will be going through an overview on CHIPS Alliance as well as details on the SweRV EH2, EL2 core. Michael from Antmicro will be going over tools that are available, and I really want to give him a special thanks. He's actually in Poland, and it's 2 o'clock or so in the morning, so thumbs up and really appreciate his support. Steve from Codasip will be going through some of the commercial support that's available. And Dan from Metrics will be going over some cloud-based verification tools. And I think, have I gotten everyone or did I miss anyone? I think that's it.
That might be it so far, yeah.
Okay, yeah. So with that, I'm going to hand it over to Zvonimir. Do you want to share the screen or do you have his presentation? How do you want to do this, Jeffro?
It's the easiest if he shares his own screen. Are you ready to share?
Okay, sure.
Okay, great. And so also look in the chat window, I'll be putting each of the presentations. So if for some reason, the bandwidth isn't really not working well for you, you can follow on the presentation slides.
All right, and tell me if I'm nicely sharing over the whole screen.
You are sharing the whole PowerPoint window.
Yeah, we can see it. There you go.
There you go. It's perfect.
All right. All right. So good afternoon, everybody. And I don't know what to tell to Michael. Good morning. Good evening.
Good night. I don't know either.
Yeah. Good late evening in Poland. Thank you very much for coming for the meetup. I'll be providing introduction about SweRV's cores roadmap in CHIPS Alliance, as well as brief introduction to RISC-V history and RISC-V cores, as well as brief introduction to CHIPS Alliance as well. So here is the agenda. So I'll go over Western Digital and RISC-V history, over CHIPS Alliance organization. I'll introduce the SweRV Cores roadmap and the CHIPS Alliance organization. And then Robert Golla, our chief architect of RISC-V Cores in Western Digital, will take over and will present on the SweRV EH1 core recap, architecture, microarchitecture performance, and he'll also explain details of SweRV EH2 and EL2, how are these cores really different, what is new. And if we stay on a timeline, I'll explain a little bit towards the end how we are applying this core in our flash controllers for solid-state disk drives, and conclude. So Western Digital and RISC-V history. We started our history in 2014, 2015 timeframe. We had a summer intern from UC Berkeley. We got first introduced to this concept of the open source core, of the cores that you can design and modify by yourself, but find good software support. And we got fairly interested in it, both from perspective of having a rich ecosystem of RISC-V companies on which you can get interfaces to various innovations for storage and memory and other smart peripherals. as well as exploring design freedom that comes from owning your own compute cores. In 2017, we announced plans to ship 1 billion cores, you'll probably hear more from us about this later this year. In 2018, we become, in this time period, we became very active in the area of open source software around RISC-V, as well as open source hardware. We announced a bunch of open source cores, including SweRV EH1, and now SweRV EH2 and EL2. We open sourced the OmniExtend cache coherence over Ethernet protocol, and we also announced a bunch of partnerships with numbers of other companies. Bulk of these activities that specifically relate to open source hardware, they're on the different nature than your normal Linux-based open source software activities. And there was a need in the industry for the organization that would host and guide these activities, that would provide sort of initial velocity for many of these projects, and enable companies interested in taking advantage of open source hardware to sort of develop the seeds of future projects. So we started an organization called CHIPS Alliance, and this is an organization that you should think about it mentally. If you have to explain it to somebody what is a CHIPS Alliance, you can think of it mentally as a Linux foundation of open source hardware. It's really trying to be to hardware what Linux operating system is to software. It's trying to build the basis for a bunch of open source hardware, and it's trying to provide compiler tools as well along the way, similarly as GNU provided a compiler for Linux kernel. So this is an organization that develops and hosts open source hardware code like IP cores, think open source CPUs, and then open source software design tools, think of, compiler tools that will take some Verilog IP and make it into a hardware, as well as interconnect IP that sort of puts things together. This could be a bunch of physical and logical protocols as well. It's meant to be a barrier-free environment for collaboration that has a standards organization framework very similar to the RISC-V, and it follows Apache v2 licensing model for its legal framework. And obviously, the idea is to share resources, dollar, and time, which lower the cost of hardware development. Sometimes a better, different way of saying who we are is just to sort of show the logos of members. In terms of goals and deliverables, well, goals are to lower the cost of development and to leverage common IP such as RISC-V cores, but also neural network accelerators, on-core components, interconnects, and as well as to develop open source software design tools, which are really very important in developing open source hardware to sort of enable easier sharing of information and resources in open source hardware projects. And the general idea is to have open source collaboration that can now benefit hardware as well. To design the open source RTL that enables different purpose-built solutions from IoT to edge to data center. Think like specific accelerators for new artificial intelligence workloads. And to also foster new business model development and promotion of open source policies. Like a recent partnership that Western Digital, for example, has done with Western Digital, where Codasip is actually officially providing technical 24/7 customer technical support for SweRV family of cores, while the actual IP of the cores is open source and sits on CHIPS Alliance GitHub. In terms of work groups that are currently active in CHIPS Alliance, we have a Chisel workgroup that is the largest one and hosts the open source design tools for hardware development based on Chisel. Has about 40 plus developers. Interconnect workgroup that's hosts the Tilink 2.0 cache coherence protocol from Berkeley, AIB chiplets open source 5 from Intel, and OmniExtend cache coherence protocol, which actually packs Tilink on Ethernet. There is a Rocket SoC group that hosts a Rocket SoC generator that originated from Berkeley. Then the Cores work group that hosts the family of SweRV Cores. And finally, Tools work group that has open source RTL simulator called Verilator, Fuse SoC Package Manager, and Coco TV Verilator project. And this is the sort of roadmap of open source RISC-V cores from many different places, including ETH Zurich, Berkeley, and also now CHIPS Alliance. We released core SweRV EH2 at the end of 2019. And this is still an active project. And recently we released SweRV EH2 and EL2, which are the subject of this presentation, and they are now available in CHIPS Alliance. In terms of GitHub links, I think Ted will post them in a chat box. So these are the links for the GitHub CHIPS Alliance, as well as cores, BoD generations, instruction set simulator, and SweRV FPGA Fuse SoC-based package manager, which is very useful to get you quickly started on synthesizing FPGA images, and a Nexus A7 popular board is supported. And then a little bit of detail before Robert takes over. In our first generation core, we focused on 28 nanometer TSMC technology, and we released SweRV EH2. That was a superscalar 9-stage high performance dual issue core. In a second generation, we created the SweRV EH2, which is an upgrade of EH1. Now it's targeting 16 nanometer TSMC. And it's a first sort of professionally design verified open source RISC-V core that supports multi-threading. So it supports 2 threads on top of the dual issue pipe, and presents itself as a very attractive solution for a variety of real-time systems that can take advantage of multi-threading. And then we also released the tiny core SweRV EL2. It's a small 4-stage core, also targeting 16 nanometer TSMC, targeting different general purpose finite state machines and microcontrollers for SoCs. All right, and I'll let Robert take over from here. And Robert, I can continue hosting the slides if you want. Just tell me roughly next.
Yeah. Can you hear me, please? Yeah, you go ahead and host the slides. I think that'll be best. So just to give a can you hear me okay?
Maybe Robert, hold on a quick second. So Zvonimir or Sri or Robert, so there was a question that's open. It's the mass would be the key document to understand the microarchitecture. So do you guys want to, is that something you can answer, or should we just type the response?
I can type I'll go and check all the questions, and
okay.
And I'll go into a chat box and answer.
Okay, okay.
I put the Q&A box in the middle of my screen. Am I still nicely sharing the slide, or I have like a dark gray box somewhere?
No. You can see the screen just fine.
All right, cool. All right.
Okay, Robert, go ahead.
Okay, so just to give a recap, the first core that we did at Western Digital, the first RISC-V core, was the EH1 core. And like Zvonimir said, that's been out there for, I think we finished that in late 2018. It's been out there early 2019. So it was an 8-stage pipeline from fetch to commit. Basically, the design goal for this core was to address the embedded market. It was a RISC-V 32-bit core. It supported the IMC extensions, integer, multiply, divide, compression, compressed ops. And the goal was to build the best dual issue core that we could, achieve the highest performance we could, given that it was in order, and do it in the smallest area footprint, least complexity that we could. So we came up with this pipeline. Basically, the first 2 stages, we access internal memories. We can support either an iCache or internal iCache closely coupled memory, or both. We can access both to get the instructions. We have 1 cycle to do the alignment. So because we have compression, you have to figure out where the instruction boundaries are. Of course, RISC-V makes that pretty easy. And then we can decode up to 2 instructions, which we send down basically 5 different pipes. And so we have a load store pipe, and the load to use latency here from loads to stores or other loads is 2 cycles. And then if you have a load to an add, we had this idea of primary and secondary adders. And so with that concept, you can actually have a 0 cycle, 1, 2, or 3 load to use latency. The multiply pipe is 3 cycles, it's fully pipelined, and then the divider was a 34 cycle out of pipe. So it was blocking. When you do a divide, it's blocking the pipes. Since it's single thread, we do non-blocking up to, it's a build argument, but typically you would have 8 non-blocking loads that you could have outstanding at a time to the external bus. And in this architecture though, the pipe itself, if you had it, we weren't able to determine we were going to the external bus until DC3. So if you had dependence behind it, it blocked until that result would come back. And we sort of addressed that in the 2nd generation cores. So single thread, that wasn't a big issue, but it became a bigger issue for some of the things we wanted to do on 2nd gen cores. And so the core mark per score for this was 4.9 core marks per megahertz. And, you know, versus the competition, you know, when it came out, I think it's pretty decent. Compared it to ARM and some of the Boom cores, as well as even the Intel out-of-order cores. Of course, core mark is an embedded benchmark, so it's not going to highlight all the out-of-order performance you can get from an out-of-order pipe. So I think that's good enough for this. Next.
Zvonimir, you got to move it. There you
I
go.
think I did.
Yep.
There's a delay of a few seconds, so just I pushed the button immediately.
So for our 2nd gen cores, basically in our internal use cases, you don't always need a large core. A lot of times you're more interested in a smaller core, something that is good enough, but has a much smaller area, much smaller cost, much lower power envelope. So we designed this sort of EL2 core, and it's kind of in the class of what an ARC-EM core would be. It is a 2nd generation design based on EH1. It's also RISC-V 32-bit IMC. We added the bit manip extensions to it, the ZBB, ZBS. It's not 8 stages to pipe to commit, it's 4 stages. It's a true non-blocking microarchitecture, so that follows from 2nd gen cores. And so what I mean by that is a load will basically, when you go out to the external bus, if there's a dependent behind it, it doesn't block the pipe from other operations. And in addition, the divide itself is non-blocking on this architecture. So a divide won't block unless you have a consumer of that divide, otherwise you keep going. The general design for this core was as long as you're running from the internal memories. Now the internal memories could be closely coupled memories, which we support, like a data closely coupled memory, or it could be an instruction closely coupled memory or an instruction cache. And so for the closely coupled memories, the sizes that we support are 4 kilobytes all the way up to 512 kilobytes. And they go up in powers of 2. And for the iCache, we support 16 kilobytes all the way up to 256 kilobytes. So for the ICSIM and the iCache, you can have both, one or the other, or none. For the DCSIM, you can have it or not have it. So you can kind of choose what you want. We have a program linter controller that we leveraged from EH1. It supports 1 to 255 interrupts. It has basically, for every interrupt pin, you can choose whether it's inverting or not, whether it's level or edge triggered. You have 4 priority levels, and you have an enable pin. We support the RISC-V debug standard. And in addition, on our ports, our main ports, we're a Harvard bus architecture. We have a bus master for the loads and stores, a bus master for fetch, and we support the system bus port from the RISC-V debug spec. So while the core is running, you can use the debugger to access external memory and see what's going on. Because we have these closely coupled memories, we also have a DMA slave port, and the DMA slave port can go in and read and write to the closely coupled memories. This can happen while the core is running. Other things I want to say is that we designed it to run, it's a single issue machine, so it can only run an IPC of 1. But as long as you're hitting to your internal memories, then we designed the machine to run as close to 1 IPC as we can. So as a result, it tends to have a slightly higher IPC than some of the competitors in this class. We have a 1-cycle branch mispredict penalty because all the execution is done in the 2nd stage of the pipe. It's a pretty basic machine, but we also added a 0-cycle branch target buffer to hide that 1-cycle CPI loss. And then on the load to use, the load to use here is 1 cycle. So generally speaking, if you're hitting to your CCMs, you're going to be 0.9 to 1, that kind of range. We also added, we enhanced the interrupt latency from first gen. So in second gen cores, you have the option to build in fast interrupt support. So in first gen cores, when you get an interrupt, it goes through a prioritization process. You pick a winner, you present it to the core, it jumps to an interrupt service routine. We look back to see which of the pins caused it, and then we compute a jump address, and then we jump to the corresponding interrupt service routine. With this fast interrupt support, we skip that first interrupt and the interrupt service routine. We just look up where we need to go, and we jump directly there. So that's part of the fast interrupt support. We also enhanced the DMA support. In the first generation cores, they weren't fully piped for reads and writes, and now they are. And in addition, with this non-blocking architecture, your latency to get in and out is faster because you're not going to be blocking if you have a non-blocking load. Dry stone score on this core is 2.0. Core marks per megahertz is 3.6. And it runs at 600 megahertz in a 16 nanometer worst case corner at TSMC's process. So that's the little core. So this is EH2, and it's the big core, and this is in 16 nanometer process. The little core is about 1/3 the size of this core, and this core is about 40% the size of EH1. Of course, it's in a newer process, so those are kind of rough ballpark numbers. But this is also second generation design, leveraged from EH1. It added atomics in addition to what, it added atomics because we had the 2 threads, and we have the same bit manip extensions. It's the same 8-stage pipe to commit, and as I previously explained, it's a non-blocking architecture, so it's fully non-blocking. So if one thread misses out to memory and there's a dependent right behind it, hardware will take care of it and clear the pipe so the other thread has full access to the pipe. You don't have to build in the multi-thread support. You can build it for single thread only, or you can build it with dual thread. When you build it for two threads, this machine is designed to run as high a multi-thread IPC as possible. So basically, there's a lot of different algorithms that we use to make sure that the 2 threads maximize the utilization of the pipeline, okay? And in this particular design, we're pretty well suited for it because we have 2 different, as we already talked about, we have 2 pipes, I0 pipe, I1 pipe, with all the execution resources there. The one thing that will limit this is the load store pipe, because once you exceed 100% utilization of load store pipe, you can't scale anymore. So that's typically what you see in high IPC workloads. So if you start out with a single thread of 1.5, you're not going to have much more room to get throughput gains. Same fast interrupt support, same enhanced DMA support. The dry stone on this machine is 2.9. Core marks per megahertz is 4.9 for 1 thread. It's 6.3 for 2 threads, but of course that's actually a little bit higher now. And the target runs at 1.2 gigahertz at a 16 nanometer worst case corner. And in terms of internal memories and all the rest, it's very similar, same basic external stuff as the EL2 core. Okay, next one, right? Okay, so how do we thread the pipe? And one of the things in threading is you have to pay very close attention to where you have your stall points. Because where a pipe stalls, typically when you thread it, you basically have to duplicate microarchitectural state and you have to duplicate architectural state. You always have to duplicate architectural state. So when you thread a machine, all the architectural state gets replicated. So in the case of RISC-V, that's all your integer registers, of which there are 31, as well as all your control and status registers and anything else having to do with the architecture. Now in terms of microarchitectural state, where you have 2 threads vying for a resource, you end up cloning the microarchitectural state. So before the iCache or the instructions closely coupled memory, we duplicate the 2 fetch address registers, okay? And then basically, you could be missing out to the external bus, in which case you're not ready. But assuming that you are ready, then you would come down the pipe. If both threads are ready, we use an LRU bit. We call it a favor bit to pick which one of these to put down the pipe. And in that case, we'll then toggle it to favor the other thread the next cycle. So basically, there's an arbiter between the fetch addresses, and that determines who gets to access the caches to get instructions down the pipe. And so a lot of the things in the pipe are shared, and some of the things have to be duplicated. At a core level, the growth in area might be like 35–40%, but when you add in the memories, oftentimes the core is only 10 to 20% of the total size of the core with the CCMs and the iCache and such. So, and in practice, oftentimes this cost of threading is less than 10%. So, and in most applications, I think we're going to see a bit later, most applications in the real world, you're going to get a sizable gain. You're going to get like a very nice gain from the second thread. So that's sort of the allure of doing threading. So carrying this forward, before the aligner, we have 2 fetch buffers, 1 for each thread, and because that's a stall point, you don't know you have all the bytes for an instruction, for example, we have to arbitrate between the 2. You know, if only one's ready, it's clear that one was going to come down the pipe, and if both are ready, they're both going to come down the pipe. And then after the aligner, we have the instruction buffers, which are cloned for each of the threads. And once again, that's a stall point, so if one or the other is ready, then we'll send it down the pipe. But really, decode is where we try to make the best possible decisions on how to keep the pipe utilized. So decode is actually aware, like if we had 2 loads, there's only 1 load store unit. So the load that's favored would go down the pipe, but we know the other load can't go down the pipe, so we'll give the whole pipe to the first thread, and so he'll be able to send 2 instructions down the pipe if he can. We do the same thing with multiplies. If we have 2 multiplies, the favored one will go down the pipe, and then the second one will not, but we'll still allow that, or the favored thread to have a second instruction down the pipe. We take into account loads that miss out on the external bus. We know the thread will be busy, so we'll basically take it out of the ready pool and let the other thread have full access to the pipe. We take into account divides. If there's a divide stall, even though it's non-blocking, you can still have a consumer of the divide, or you can even have a second divide. And since we only have 1 divider, that can be a divide stall. We'll give up that. We'll take that thread out of the ready pool and let the other thread have full access to the pipe. We take into account pre-syncs and post-syncs and some things like secondary stalls. So when we know a thread is going to be stalled 2 or more cycles, we will basically optimize the thread scheduling to favor the other thread. And in that sense, you kind of get the best possible multi-threading. So just to add a little bit more, each thread has 4 fetch buffers. They're 8 bytes wide. And I'll talk a little bit more on the next slide. The other thing is each cycle we're trying to pick, if both threads are ready, typically we're trying to pick 1 from each thread, okay? And because that maximizes your throughput if you pick 1 from each thread. You can consider some examples like, in general, the oldest, you know, when you're picking between each thread, you're kind of getting the oldest instruction at that point in time, so there's less speculation. That's one thing. But the second thing is threads can have serial components, right? And so if you're running serial components and you actually can pick both threads to go down the pipe, you can run that at 2 IPC. Whereas you only pick 1 thread or the other, you can limit yourself to only 1 IPC. So in general, if we have 2 threads ready, we're always sending 2 threads down the pipe. And there's an example of that later. Yeah, I think that's pretty much it.
Robert, you got about 5 minutes.
I can do it in 5 minutes. I got 2
Yeah, I
slides.
know. I know.
So this is kind of a threading diagram. So this kind of shows what I was talking about with the threads. So this is how the threads would actually flow down the pipe. So in this example, thread 0 is green, thread 1 is red. You got 2 of them ready at fetch, and the favor bit points to green, so that's the one that went to fetch 1. The previous cycle would have been red. These 2 pipes, there's only 1 thread per stage, so we call that vertically threaded. At the align stage, there can be 2 threads present, and that's because there's 2 fetch buffers there, and they both could have instructions ready to go down to decode. And originally there was an arbiter there, but we actually optimized this out to get more bandwidth. So since we always had 2 aligners, we were actually able to align 2 threads in parallel and fill the instruction buffers down at decode. So we got rid of the arbiter there and we got more bandwidth. And then at decode, we have a thread arbiter to choose between the 2 threads to send down the pipe. And like I talked about, generally we try to pick 2 threads. So you see reds and greens going down the pipe. What's a little less obvious though is the I0 pipe is not symmetric with the I1 pipe. And so because of that, when 2 threads are ready, we will oscillate to make sure that the threads can actually get onto the I0 pipe, which can execute all instructions, whereas I1 pipe can execute most instructions. And the last point I make is whatever is decoded, whatever that group is, that's what's going to flow down the pipe, and that's the way it's going to commit. So the commit group will be the same as the decode group. Okay, next slide. How much time I got now, Ted?
3 minutes, probably 3.5.
3.5, all right. So anyway, this is an example of threading. So when you look at this, there are many different, this is coarse grain threading. There's also fine grain threading, but this is an example sort of coarse grain threading. So this is for an application called matrix sort. It's one of the little C programs that we run. And if you were to run this in single thread, you're running out from the bus, and the bus has a load to use latency of 11 cycles of this example. So when you look at this and you're running single thread, everywhere you see the red, those would actually just be bubbles. There would be no instructions there. It would be a delay while you waited for those load results to come back so you could then feed it to the branch, okay? So when you add the second thread, which is the red thread, you run the same program on the other thread. What happens is that in this case, it naturally fills in all the bubbles. So you move from an IPC of 0.79 for single thread to an IPC of 1.5. And so that ends up being a multi-thread speed up of 1.9x. And I have a slide coming up showing a bunch of different combinations of this. So, but this is the general idea of threading. You're trying to fill in the bubbles. Try to get to a higher IPC than you can get through single thread alone. Next. Okay. So for EL2, I've already mentioned IPC on this that hit to the internal memories. The IPC is going to be close to 1. As practical examples, CoreMark runs at an IPC of 0.95, DriveStone runs at an IPC of 0.98, and virtually all the little C programs that we run that run from internal memories, they run in the 0.9 something, okay? And the microarchitecture is designed to run at 1, so I think it's doing pretty good. Single thread on EH2, if you build it, it's going to be essentially the same as EH1. There haven't been significant improvements in that single thread, but the big thing is multi-thread performance. So we generated like 120 different kinds of workloads. We took a bunch of different C programs. We ran it from the internal memory. We ran it from the external bus with 0 wait states, 10 wait states, and 20 wait states. And then we generated all this single thread runs, and that's what's plotted on the x-axis, is single thread. And then we took a copy and ran it on the other thread, and that generated the multi-thread IPC, and that's on the y-axis. So the point of this exercise was to try to get a sense under all conditions how our threading would kind of work. So basically, if you're less than 1, ideally you would like to always double your performance, and this is sort of dashed green line marked ideal. And when we're below 0.5 IPC, there's no issues with load store utilization, so we do a very good job lining up with that ideal. As we get between 0.5 and 1 on the single thread, sometimes we run into issues with the load store and you see sort of a trailing off. And then above 1, it's a little bit of a crapshoot because as you get up higher above 1, you can no longer be better than 2 because we're a dual issue machine. But in general, where you see those bubbles coming down or the red marks that are lower than the ideal, it's generally because we've oversubscribed the load store unit. So less than 0.5, our average multi-thread speedup was 1.95x. And in actuality, a lot of real-world applications, because they actually do go off on the external bus, and they don't all run from internal memories. They typically will have IPCs around 0.5, which is why we're pretty confident in this threading architecture. But between 0.5 and 1, we have an average speedup of 1.83. Between 1 and 1.5, it's obviously going to go down because we're already utilizing a lot of the pipe in single thread. It's 1.36. And 1.5 to 2, I mean, you're limited in how much more gain you get there. It's 13% in this example. And I think that's it.
All right, so in interest of time, I'll skip this slide and put the conclusion slide. We had a bunch of questions on the both chat and Q&A. We tried to answer that. Anyway, to conclude, we are sort of threading strong into producing open source RISC-V cores. 2 generations of cores have been released. We are using them inside the Western Digital products. You'll probably hear more of us about it later this year. The RTL of the cores is shared on a GitLab a GitHub of CHIPS Alliance, and I think we posted the links in chat box as well as in this presentation, which is actually available as well on its own. So.
Yes, thank you.
Right.
Thank you, Zvonimir. So hopefully everybody that is in the audience has a great overview on the EH2 and EL2, the new cores. If you have questions, I definitely encourage you to put it in the Q&A. We'll get to them. But now I want to turn it over to Michael Gielda from Antmicro. Again, really appreciate, Michael, you staying up because I know it's super late for you. And as Zvonimir said earlier, I don't know whether to say good morning or good night, if you have your presentation ready, why don't you share your screen and you have the floor.
All right, let me just share my screen and okay. Can you all see it now?
Yes.
It's good.
Perfect. Right. Hi. Welcome. So yeah, it's 3 a.m. indeed. So if I slip my tongue or forget what I was saying, then obviously you have to excuse me. So today I'll tell you about SweRV and the open source tooling ecosystem around it. And I'm Michael Gielda. I'm of course part of a company called Antmicro. I'm VP Business Development there. I also happen to be the chair of marketing for CHIPS. So now I'm talking with both hats on in a sense, but fortunately these interests and those ideas are very well aligned between both my company and CHIPS Alliance, which we're also part of. So short introduction where I'm coming from. My company does all sorts of different open hardware and software things, starting with proof of concepts, demonstrators, and prototypes, as well as hardware devices using RISC-V. Then we'd also do software, different kinds of software like operating systems, BSPs, device management systems, you name it. Another thing that we get involved with very often, and this is getting closer to the topic of this presentation, is custom FPGA IPs and system packages, soft system on chips. So generally speaking, more hardware-oriented work. But what I'll be talking about today is actually the fourth area, which is tools and software methodologies, and hardware methodologies as well, for developing RISC-V based systems. And of course, this area kind of feeds all the other areas because it's a meta field where all the tools that we're developing and we're helping customers achieve some kind of improvements in their workflow. And obviously, we're also improving our own workflows in the same process. And that's the great thing about open source. As you're building out the open source tooling ecosystem, you end up benefiting everyone. So what Antmicro does in the tools area is we provide services to develop different kinds of tools, both for ASIC and FPGA development. And since we're quite deeply involved in this ecosystem, both in RISC-V and chips and Linux in general, we can help kind of aggregate and combine and add on top of existing efforts to achieve a good result. So we always say that we help other people develop, ecosystems around open silicon, which CHIPS is very much interested in. And we do that through both our own open source frameworks as well as contributions to external ones and integrating things together and improving workflows. And we believe that open source improves scalability. It enables you to automate your workflow and it gives you full control of what you're doing. So this particular aspect of control and openness and security I think is growing in importance, and we think it's one of the key reasons why we choose open source. So it's a very pragmatic approach to open source. So today I'll be talking about SweRV, and that is actually pretty simple to work with it because it comes with an ecosystem of tools around it. This is a dynamic, of course, and growing ecosystem. There's a lot of building blocks that are already in place. There are others that are being developed. So I'll start with talking about how you can just, get started very quickly by simulating SweRV in something like Verilator. Then I'll move through how do you actually use SweRV in practice and put it on an FPGA and perhaps combine it with other things using tools like FuseSock and Utilize. Then, of course, all of you know that a core is not enough to do the job. If you want to build a practical system, you need a system on chip. And I'll tell you a little bit about Litex, which is a system of chip generator that enables you to take SweRV and put it in an actual practical use case. I'll kind of skip over the, software part of things. I mean, by now, hopefully all of you know that, GCC, GDB, OpenOCD, Zephyr, Platform.io, all of these things are there. They work with RISC-V. They obviously work with SweRV. Some of these developments have actually been heavily supported by Western Digital. So SweRV actually comes with excellent, kind of software and IDE support and so on. But this is a topic for a presentation of its own. So I didn't want to kind of take up the time in that area, because I'll be focusing more on tools that are like relevant to chips and the activity of chips in the tooling area. Next up in my presentation will be kind of telling you about Renode, which is a simulator that Antmicro is building, which allows you to co-develop hardware and software together and build real applications. Then I'll move over to what kind of tools you'd use if you wanted to build a production grade ASIC and verify it, and that'll be the RISC-V design verification framework and the Whisper ISS. And I'll finish off with a look into the future and some of the developments that we're working with in terms of improving development flows for ASIC design, especially around system Verilog. So let me dive into those topics one by one. Verilator is, of course, a brand that everyone knows. It's one of the most successful, open source EDA-related projects. It allows you to simulate your RTL with high performance, and it does that by compiling it into an optimized model and running it. And of course, it supports all of the SweRV cores. You can just go to the READMEs of those projects, and you'll be able to run Verilator. So while I'm talking, you could even go to GitHub, download SweRV, and run it in Verilator. That's the awesomeness of Verilator, is that it just comes for free. Just get it from GitHub, and that's it. It has other features. It can do linting, and importantly, it's not just any open source. It actually outperforms many of the proprietary alternatives. And I think what's important to mention about Verilator as well in the CHIPS Alliance and Western Digital context is that it is actually developing rapidly. There is quite a lot of work going into it from both the author, Wilson Snyder, the general FOSSI community, free and open source silicon community, and most significantly the CHIPS Alliance, and Antmicro currently is involved with supporting system Verilog and UVM inside of Verilator. And that work is kind of co-funded by other CHIPS members, including Western Digital. So there is a dedication on the side of CHIPS Alliance. There is real work going into making that tool better for the kind of use cases you'll encounter while working with SweRV. Fuse SoC is a tool that will actually enable you to grab SweRV and put it in the context of other IPs. It's a package manager that's also kind of well supported with SweRV, and it enables you to reuse your work across many designs. It's a configuration-based utility. It's Python-based manager, and then you can basically take different kinds of building blocks and put them together. And it enables you to kind of both reuse components, let other people reuse your components, set up configurable continuous integration systems, and easily port between different targets, especially like different FPGAs that you might want to run your system on. Recently, FuseSoC is actually switching to BSD. I don't know if the switch is actually complete, but this is going to happen. So it's getting a very nice and commercial-friendly license. And as an example of how you could use FuseSoC, there's an SoC called SweRV that uses FuseSoC to just assemble together a bunch of IPs in the core, and that's SweRV. So Fuse SoC, as the name implies, can be used to build an SoC. Another tool in that vein is Edelweiss, and that'll be a very common theme. While putting together this presentation, I came up with the idea that we should probably have a dedicated CHIPS Alliance logo fund, because many of the tools I'm talking about just don't have a logo. So I took this icon that one of our graphic designers proposed for the idea of modularity and ability to replace different kinds of tools in the workflow. And here it is. This is not the Edelweiss logo. And this is, again, a Python utility, which allows you to work with different kinds of EDA tools, both for FPGA and ASIC design. and you can kind of abstract out the variation in the way the tools work. And it helps you to pinpoint whether your bug is really kind of tool related or it's more just your code. And it just lets you work with different kinds of tools and choosing the right tool without having to care about the details. It's a neat little utility that kind of fills in some holes, and we're using quite a lot. We're contributing to it as well. One big highlight to mention, I think, is LiteX. This is going into the, what could you buckle on top of SweRV to actually make it a full-blown system. The LiteX is an SoC builder. It's in kind of IP library. And as you can see on this picture, there's quite a bunch of IPs that LiteX has in it. All of these things here on this diagram, so both like a DRAM controller, Ethernet, USB, PCI Express, SATA, SD card, all of that stuff can be found in the LiteX repositories. And you can basically take those building blocks and just configure them to work together with it actually works with different kinds of CPUs. But there is initial SweRV support, and having this support enables you to quickly build plug-and-play SoC systems with SweRV. And the cool thing about LiteX is that we're putting in a lot of work to make it, to surround it with a robust software ecosystem. So LiteX can actually run Zephyr. If it has a Linux-capable CPU in it, you can also run Linux. There's drivers for all these peripherals. It runs in Renode or simulator. You can run it in Verilator as well. So you'll be able to run the models of those peripherals in Verilator. You can also use it with SymbiFlow, which is an open source FPGA flow. So there's quite a lot of work going into that ecosystem. And by just plugging into the LiteX ecosystem, you get quite a lot of benefit. And the fact that there is initial SweRV support is very helpful for kind of tying those ecosystems together. Now, if you want to go, you have an SoC, and now you want to go and build something concrete and perhaps experiment a little bit with architecture and co-develop hardware and software. So Antmicro built this framework called Renode that's used for simulating things. And the important thing to know about it is that it allows you to rapidly create and experiment and develop software for pretty complex systems. So I don't just mean the core, but I mean entire SoCs or even kind of boards or systems of boards. And all of this can be done without actually changing and recompiling the simulator itself. You just grab the simulator, you download it from the web, and it's open source, of course. And you put together a bunch of configuration files, and you're done. And this allows you to execute, debug, and test software very effectively. And since we have a lot of features geared at this debugging and testing capability, and also we integrate with a bunch of tools in the open source domain, that gives us quite a lot of capabilities as compared to real hardware. And since we're capable of heterogeneous multi-core systems and so on, you can see how it will scale as the SweRV family grows. You could see those little boxes on the diagram Zvonimir showed. We're ready to handle that. And of course, I like to have something to announce when I'm giving a talk. So yes, we have initial support for the SweRV EH2. And I'm pretty sure the other cores are not very far away, but we've recently added the EH1 support, so you can go check it out. As I mentioned, LiteX is also supported in Renode, so you can build system on chips with peripherals, with Ethernet, with other kinds of IPs, and also simulate that in Renode. And if you want to run the real HDL for some kind of a specific accelerator or IP in your system on chip, you can also co-simulate with Verilator. So you run most of your system in Renode and then a part of your system in Verilator, and you just kind of execute them together, and it works. And Renode, if you're kind of wondering, okay, what would you use Renode for, is being used for porting operating systems. So for example, SL4, the security-oriented system, was ported for RISC-V using Renode. Different kinds of RTOSes use it for CI testing. So for example, Zephyr uses it for testing the TSN capabilities of the operating system. TensorFlow Lite from Google is using Renode for testing and benchmarking AI flows on microcontrollers. This is actually pretty interesting in the SweRV context, but we haven't done work with SweRV specifically in that domain yet. It's being used for hardware software co-development. As I mentioned, there's a link to a nice use case with Dover Microsystems. and of course, it's being used for other things too. And here you get a screen of Renode actually running SweRV. So on top right, there's the Renode console called the monitor. Top left, you'll see a log of the execution. And on the bottom right, you'll see the actual UART saying, hello world, yeah, you're running SweRWolf and putting Zephyr on it. Staying in the ISS domain, Whisper is a dedicated ISS that was built for SweRV by Western Digital. And this is meant to verify SweRV implementations. You can run it both interactively and just single step through code and inspect and modify stuff to see whether the execution is as you think it should be. Or you can run it lockstep with something like Verilator to compare if your RTL design is actually correct. With reference to the golden model, so the SweRV being the golden model. So that's kind of Whisper. It's one of the many ISS actually supported for RISC-V and SweRV. And again, staying in this kind of how would you verify that your implementation is correct, there's an entire flow called RISC-V DV, which is based on an instruction generator that allows you to, do different kinds of tests on a SweRV-based design. Obviously, it's not limited to SweRV, but it works well with SweRV. It's been tested with SweRV. It's based on System Verilog and UVM, so it's kind of industry standard methodology. And what it does is it runs ISSs and RTL simulators in tandem and compares the results. Of course, it's not as simple as that. It actually has a lot of dedicated test suites for different kinds of things listed on the right. So it basically is a great start if you want to verify a core. That's a full-blown framework originally created by Google, but now developed as part of CHIPS Alliance, which allows you to really stress test your design pretty neatly. And Antmicro is now working to enable a fully open flow because the original framework did not support anything fully open source. You had to have a proprietary RTL simulator license to run it. So this is going to change hopefully soon, and I'll tell you about it in a second.
Michael, you got just under 5 minutes.
I'm finishing, so it's
yeah. You got good timing. I just making sure you know.
So kind of heading towards the end, to give you a glimpse into the future, there's a whole effort around enabling System Verilog support in open source tooling. I mentioned that before talking about Verilator, but if you take a look, actually I can kind of put this in front of you in bigger form. We're building a System Verilog test suite that allows you to kind of stress test different kinds of designs against different tools, or other tools against designs. So as you can see on as columns, you have different kinds of open source tools. And on the left, you have different designs, including SweRV. Actually, the one I selected for this screenshot is a SweRV test. And as you can see, like we're improving the support, but we're not done yet. There's quite a bunch of things to work with. But we have, for example, SureLog, which is a full-blown System Verilog parser that actually can take in SweRV and fully process it. And as you can see, Verilator obviously supports it. There's another parser that also works with it. So over time, you can expect those places to go green. And Antmicro is developing this test suite with help from the community to just measure how well we're doing, right? Where we are and what to improve. Everyone that saw this framework was very happy to see it because, there's a lot of efforts, but they're very distributed. People don't really know which tool actually works well and which doesn't. Well, now they do. Now there's an actual test framework that will tell you that, and this is also being actively developed. So I think the last thing I wanted to mention is in terms of you're interested in parsing System Verilog, and obviously the reason why we want to parse System Verilog is UVM, is design verification, is enabling flows that people are used to having, but in the open source domain. So there's two parsers I wanted to highlight here that can do System Verilog. One is SureLog, which is more oriented towards kind of simulation and UVM and generally speaking, full-blown usage for various applications. This is being developed in collaboration between Google and Antmicro, and we're hoping to plug this into various open source tools as the system Verilog front end for those tools. There's also a specific Google parser called Variable that was released recently, and that parser is very good at linting and formatting code. And we recently wrote a blog note about linting and formatting a system Verilog using FuseSock. So go ahead and check it if you want. Summarizing, SweRV is not just a family of cores that's well tested. I mean, that would already be pretty incredible, but it also taps into a very good ecosystem and also kind of improves that ecosystem by being a very good reference implementation. And CHIPS Alliance is aiming to kind of revolutionize the way people work with ASICs and FPGAs, and Antmicro's very well aligned with this goal. So you can use our services to just build something on top of SweRV using this kind of new methodology, this new collaborative way of doing things. And if you're hesitating what to do next, well, first just use SweRV, take Verilator and run it and start contributing to the ecosystem. If you're working on a project, you can reach out to us and we'll gladly help. And if you're kind of interested in these kind of developments and topics, just go and see our technology showcase. This is our technical blog, which describes these kind of technical developments. And if you want to just kind of follow us on Twitter, LinkedIn, or just look at our GitHub, that's also a good way to see all the cool things that are coming up. And of course, there are some other things I can't talk about yet, but if you watch this space, both from CHIPS and Antmicro, you'll see quite a lot of things happening in a tooling area that will hopefully blow everyone's mind in the time to come. That's all from me. Thank you very much.
Michael, thank you very much. I really appreciate you staying up. Also, just when you get a chance, Michael, check the Q&A. There was a couple of questions in there. You might want to customize the answer, or you might just want to go to sleep. So I understand it.
If they're very difficult, I'll go to sleep, yeah.
Yeah, exactly. Okay, so
I try to answer all the questions. So currently there are no open.
Okay, yeah, he might just
Zvonimir.
want to look at them. So Steve, I think you're going to up next from Codasip. So we have just 2 presentations left. Steve will go for 15 minutes, and then Dan, and then we'll Dan for metrics. So let's turn it over though to Steve at Codasip. We can see your screen.
That sounds great. Can you hear me okay?
Yes.
All right. Well, I'd like to thank you all, Michael and Zvonimir and Robert. My name's Steve Winandy, and I'm a marketing consultant with Codasip. Over the next few minutes, I'd like to build on some of the excitement around the new release of these processors that you've been learning about. These new additions, the EH2 and EL2 additions to the SweRV family, these can really help save your organization valuable resource, time, and money. I know you've heard about the IP. I would like to spend a few minutes talking about the supporting environment, specifically the SweRV Support Package, and why that's beneficial and important to you. Here's a quick summary of what we'll be covering today. We will start with a high-level overview of the SweRV Support Package and what I will refer to as the SSP for the remainder of this discussion. And I should probably apologize. My camera died, so unfortunately you don't get to look at me, but maybe that's a blessing for everybody. We will then dive a little deeper into what makes up the SweRV Support Package, starting with the software development capabilities. We'll move into some of the hardware environment details and finish up with kind of a design flow overview in the different product configurations. So I guess the takeaway is, if you remember nothing, please pay attention to the next slide, because it's really the key takeaways that I want you to understand around the Codasip SweRV Support Package. The SweRV Support Package provides everything you need to design with the EH1, EH2, and EL2 cores from Western Digital. It includes all the tools, scripts, and examples you'll need to hit the ground running. And the best part is that the SSP has been fully verified by Codasip, so you know that it's ready for commercial use. It includes a complete, easy-to-use design flow, enabling support for multiple EDA tool vendors, and it's developed to automatically include all the additional dependencies required based on your configuration choices. It includes comprehensive documentation, which can help you get to market faster. In case you need further assistance, the Pro version, which we will talk about a little more later, gives you the direct access to support personnel so you are able to work through your bottlenecks quickly. And lastly, Codasip provides additional customization and verification services for the core and the SSP. The SSP is really everything you need integrated into one complete package. So let's take a little deeper dive. As you learned earlier in the session, you have access to the Western Digital SweRV IP. But what do you do from there? What else is needed for you to deploy it in your chip? As you all know, there are many more pieces to the puzzle that you need to consider. You're going to need a software environment to develop and debug your application. You're going to need a hardware environment to develop and verify your RTL. And you have to have the documentation and support to work through any unforeseen issues. The SweRV Support Package was developed specifically to provide these tools to help you complete your design quickly. The first area we'll discuss is the software environment, the portion of the SSP. The SSP enables users to develop their software application for the core by providing the RISC-V GNU toolchain configured to produce binary programs compatible with the configuration of the SweRV cores. It includes OpenOCD to enable on-chip debugging, and the SSP offers an Eclipse IDE graphical environment to develop the user's application. The user can select a SweRV core as a target, and the SSP will generate the correct build and OpenOCD debugging configurations. So with a simple click of a button, the user can load their program into an FPGA, run it, and debug it. Moving into the hardware component of the SSP, it includes a stable version of the RTL design. This is important as it provides a solid, verified baseline to build from. These cores are continually being enhanced, and this is the beauty of the open source paradigm. However, it can introduce instability into your design cycle as some of these updates can be pretty extensive and may break some portion or portions of your design or design flow. This could require modifications to the RTL and cause significant delays in your design schedule. The SSP provides the option to use both open source or commercial tools. On the open source front, we provide additional content for the user in the form of test benches, timing constraints, and documentation. And we include an open source simulator for completeness. This gives us the opportunity to include new versions of the tool only if considered stable by Codasip. Commercial development is typically done with commercial tools. So to that point, we include the same content for commercial tools from leading vendors that can be run with one command without tweaking the settings and parameters. The bottom line is that you can add new tool support very quickly, and we are continuing to expand our support package. At this point, you might be asking yourself, is Codasip only offering an archive full of tools and scripts? This is indeed not the case. The integration of these contents is as important to us as the contents themselves. We adopted and extended an open source tool called FuSock, which you heard a lot about previously, which serves as an integrated design flow in the support package. FuSock has several functions. It understands components of RTL design, specifically, or for example, cores and peripherals, as packages. It allows a user to specify their own RTL project as a FuSock package. It understands that each package can have dependencies on other RTL packages and automates the inclusion of these dependencies for you at build time. These packages can either be distributed with a support package or they are provided via open source repositories on the internet. When you provide the definition of your RTL package to FuSock through a file called mysock, it will download all the necessary dependency packages from their locations. It will then add your user source files that you have developed, and in this way, it basically builds your RTL project in your workspace. FuSock can also run EDA tools. FuSock can also run EDA tools on any of the packages you have created. This is important as the options to run EDA processes are specified in the definition of the FuSock package, meaning you do not have to interact with the EDA tool itself. These options are unified for tools from different vendors, and we support a growing list of EDA vendors. And then finally, FuSock can translate these unified options into options specific for the vendor you choose to use. What that means is that if you decide to test a new simulator and you already have all the options for the simulator process defined in the FuSock package, You only need to change the name of the tool, and FuSoc will make sure that the options are correctly translated for the new simulator. So let's take a little bit, let's look a little further into the different production configurations. Codasip offers 2 versions of the SSP, with the first being the free version. We took the position that everything that is originally open source will remain part of the free package. This includes all software development tools, integration for open source EDA tools, and a free open source RTL simulator. The free package is aimed at students and the education user base. Support is provided via dedicated discussion forum. The other product configuration is the Pro version, which targets commercial deployment. It includes everything in the free version, plus it integrates the commercial EDA tools into the FuSoc design flow. It provides all the necessary scripts for static analysis, RTL simulation, synthesis, and equivalence checking. And you will see a good example of EDA integration in the final presentation of this meetup. It also offers direct customer support, including the ability to open support tickets and the helpline phone number to call. And Codasip is known for its many years of specializing in core design and customization. So a natural extension is to offer design customization of the SweRV Core and SSP. This is an additional service we will offer our users if they need to modify any of these products and don't have the means to do so themselves. A couple common examples of this are providing help when including a floating point unit or adding custom instructions for bit manipulation. We will be expanding our services to include verification services in the near future as well. And then to be brief and to wrap up this section of the discussion, the SweRV Support Package makes the deployment of SweRV Core simple and fast. We made the process easier by providing the design flow, which integrates the contents of the package in the environment along with rich documentation to further assist you. And we only release content that has been fully verified by Codasip, including the open source and commercial design flow contents. We offer a free version targeted for educational usage and a pro version with access to direct support for commercial use. And lastly, we provide additional support services to help you customize and verify any design modifications you require. And this concludes my portion of the talk. I want to thank you for attending and hope you found this informative. You can reach out and contact us at contact@codasip.com. And we'll now move on to the next presenter.
Yeah. Thanks, Steve. Really appreciate that. The one thing I do want to say also is that you know, we know Codasip has already engaged some customers with SweRV, so it's really terrific that we've had that you know, engagement. And let's turn it over to Metrics. So Dan and Amy from Metrics, we're going to be, you know, really going crazy here. We're going to try to do a demo live. So I'm going to turn it over to Dan and Amy, and after they're done, we'll be hanging around if people have other questions or anything else that you want to ask. So take it away, Dan.
Hello, everybody. I'm with Metrics. We're a company based in Ottawa, Canada. We're probably going to be the latest, greatest to join the CHIPS Alliance. Excited to be here tonight. We're an EDA in the cloud company. So what that means is everything we do, you don't download software, you don't license software, you don't maintain software, you don't patch. Everything you do is just engineer and verify your design. We are a company that is about 5 years old, and I'll give you a brief overview, a couple slides of what we're doing, and then Amy's going to take over and actually show you the SweRV Core simulating in the cloud. So with the cloud, what makes this work is the whole idea of having a virtual cluster. So what you see here is an overview of our environment. RTL is software, so we advocate using a DevOps kind of development there. So continuous integration using Git repo is included in the virtual cluster. Our simulator, the Metrics Cloud Simulator, we have an agreement with Avery for their verification IP. We can put virtually anything into a cluster for you. We have the idea of like a Metrics app store. We can bring in other IP, debug tools, simulators. We've written our own proprietary scheduler in the cloud because with almost unlimited availability of cores. The previous schedulers didn't seem to be able to tolerate that. After the simulations are run, you interface that using any web-based HTML5 browser. You can look at all the screens that you're going to see. Amy could do that from your smartphone, from your iPad, from your desktop, whatever. Our simulator, the reason this is important for CHIPS Alliance and for RISC-V is, as you know, I mean, one of the big advantages of RISC-V is that you can modify these cores. You can make them great. You don't have to live with a black box that's got what the vendor wants to put in there, but you don't need. You can add things like hardware modules. You can add for security. You can add it, extend the instruction set. You do a whole lot of work, and it's really cool. But, and there's the big but, I sold a lot of RISC-V processors in my life, and there's always that but. When you make those modifications, you take responsibility for verification and compliance. So what that means is when you go in and take advantage of all this stuff, you've got to take an understanding of what that means to your design project. You're going to have to verify a processor. You're going to have to run a lot of regressions, a lot of bus functional models, a lot of directed random testing. This is more than just debugging at the module level. And that's really what separates kind of a commercially grade cloud-based simulator. Everything in the simulator was built from the ground up for the cloud. So it's container-based. Has all the verification data is elastic, it's stored in the cloud. You don't have to download all this. It's got virtually everything any modern system Verilog simulator would want, and it's compliant. It's in use in major companies across the world. But what I want to talk about is what really differentiates our cloud-based simulator from the rest of the world. You're going to be hearing a lot from the big traditional EDA companies who say, oh, we're in the cloud. Oh, absolutely. Go to the Synopsys, go to the website. You'll see videos, you'll see Cadence website. Let me tell you the 3 questions to ask an EDA sales guy. Number 1, do I need a license? And if it's in the cloud, you don't need a license. The whole idea is you're only paying for use. If I ran 1,000 hours in simulation, if I had a test bench that had 1,000 test cases in it and I ran each one in parallel, what if I ran all those as one? We have customers that are taking regression tests from like 9 hours down to 1 hour. And it's totally changing the whole idea of like directed random regression tests. And that's where you find the majority of your bugs in modern and large commercial grade SoCs. So the first question is, do I need a simulation license? You shouldn't, not in the cloud. Second is, do I have a limit on storage? There's nothing worse when I was designing cores. Would come in the next morning and find out, well, we ran out of storage, so the regression stopped, so we're gonna have to restart it, and we'll come back tomorrow and see if it worked. The data needs to be elastic, which means it grows as necessary, and it should remain in the cloud. You should not sit there for an hour or two to download a giant change dump file or something like that. EDA has big outputs, and so leaving them in the cloud is much more productive for you. Most important is the SaaS business model. You don't need to acquire an asset. You don't need to buy a simulator, put it on a shelf, and use it as you do. You can simply pay for use. And you don't pay for anything while you're analyzing the data. It's only while the application is running. And your CFO and the finance and the CEO guys will get all excited because everybody's always looking for OpEx instead of CapEx. And the traditional EDA vendors will tell you, oh, a time-based license, oh, that's a OpEx because we're only leasing it. Well, see your lawyers, especially if you're a startup, because that's not true. You're acquiring an asset for a fixed time, and you're only allowed to write that off on your taxes over that fixed time. So ask these 3 questions, and that's why you'll see we highlight the word true on our screen. So what's the industry saying? Well, Qualcomm, company I know quite well, says it quite well. Let's say you had a regression test case of 20,000, or a test bench with 20,000 test cases in it. Well, you're going to have limits in your data center. It's either going to be your verification IP licenses, your SIM licenses, the number of processors you have running, but you're going to be limited. So of those 20,000, let's take and say you had 100 that you could run in parallel. So you're going to run 200 batches of 100 test cases. And if each one is a half hour long, that's 100 hours. So you've got 4 days to wait to find out, did what I check-in work? In our world, you run all that in parallel. You got 40,000, 100,000 I don't care how many you have, we're going to run them all in parallel. And you're going to be done when the longest test case completes. So if your average test case is 30 minutes and your longest is 1 hour, you run 20,000 test cases, you're going to be done in an hour. So think about the aha moment of, dang, I don't have to wait 4 days for this regression because I'm going to release my processor to the SOC team. I can do it on demand, I can run it, and I only pay for it when I use it. Second one is, you're probably, like everybody else coming back from this pandemic, you're probably going to be looking at all kinds of cost reductions. I imagine when we get back to work, the exec staffs are going to be roaming the halls looking for, how do I save money? How do I save money? Well, the quickest way is to quit buying hardware. Quit loading up tons of real estate that you have to cool, you've got to power, you've got to patch, you've got to tune the performance. Let the experts do it for you. eSilicon in here, in their data center alone, reduced their cost 20%. Bigger companies were seeing 50%. So instead of cutting engineers, instead of cutting back on new hires, cut back on the computers, pay for it in the cloud as you go, save yourself some money, and get your job done. And then everybody's like, oh no, can't put it in cloud, it's security. You know what? The guys putting men on the moon think that the cloud is safer than their own data centers. I hear that completely across the industry, where people are saying, we can't afford to secure our data center. And it really becomes a big problem when you take ownership of the IP into your data center. You're agreeing to the IP vendor to protect that RTL. Well, if it's in the cloud, you don't have that liability. It's the cloud's job to protect that. So you won't be getting a call from the lawyers at ARM when they find out that somebody hacked your their IP off of your server. So with that, I'm going to turn this over to Amy, who's going to show you the SweRV running in the cloud. This will be running on the Google Cloud. We're cloud agnostic. We can run on any cloud, but we choose a Google. So I'm going to stop here, Amy, and let you take over.
Thanks, Dan. I'm going to start sharing. All right, so I'm going to go through this a little bit quicker than usual. Hello, everyone. I'm Amy Sutton. I'm an engineer at Metrics. I'm happy to give you a quick demo of our product and answer any questions if time permits. If time doesn't permit, I'll try to put my email address in the chat window or the Q&A window, and anyone feel free to contact me after. So the diagram that we're looking at here is basically a workflow diagram. How do you work with Metrics? So Dan gave you a good overview of our product, and I'm going to give you a little bit more detail of what it's like to work with us from a user perspective. So the icon in the top left-hand corner represents your team of designer verification engineers. And this diagram shows that you have two interfaces to Metrics. The one on the right is through your web browser, and the one on the bottom is through your Git repository. So the diagram illustrates a continuous integration workflow where the act of pushing changes to your Git repository will launch a number of simulations in the cloud. And the simulations or test suite here is completely defined by the user. As Dan mentioned, when you run simulations on Metrics, they all run in parallel. And we can do this because we own the simulator, so we don't have any license restrictions, and we don't have hardware restrictions because we're using the cloud. So we have access to data center resources. So as each of these simulations finishes, the results are published to a database, which is also stored in the cloud. The database can grow to accommodate the large artifacts that simulations often produce. You never have to worry about running out of disk space or managing disk space, as we can do that and implement data retention policies for you. And then as the database is populated, the results are presented to you in our web application. So showing you the web application is going to be the focus of the demo. And the web application provides you with the tools you need to interact with your data to perform some debug, triage, make changes to your design or test bench, push those changes to Git, and then continue the cycle. Okay, so I'm going to switch over and show you what the Metrics web application looks like. So I'll start showing you our results view. So this basically gives you an overview of all the regressions or batch simulations in our database. Now this one here, Core SweRV, that's the name of the project. What I'm using is the SweRV EH2 from GitHub and the example tests that you can download for free with that Git repository. And these are the results of running those tests on the Metrix platform. And I'll show you quickly what it looks like when we launch these simulations, just because Dan said we should have a live demo here. So I'm going to choose the branch that I want to regress and the test that I'd like to run, and then just click run, and it will tell me this regression has started. So, and it's now doing a build phase. Once the build is complete, we'll be able to see the results live. In the meantime, I'll show you some results that we have from previous times that I've run these same tests. So actually there you can see the one I just started is running. The entire demo is live, running on a live Google data center. When I click, so what data are we looking at here? So we're looking at the name of the test list, the person who ran it, the branch that it was run against, the Git hash, the person who made the commit, date, time, and a summary of test status. So the number of simulations that are either pending, running, passed, failed, or incomplete. And then we've got metrics here for coverage. So our simulator, being fully System Verilog compliant, collects functional and System Verilog assertion coverage. And we present the merged results of all the tests in your test suite automatically. Now this test suite that comes with a GitHub repo has a very simple test bench. It doesn't require System Verilog and it doesn't have functional coverage. To show you what our coverage view looks like, I can show you another project. So we can of course support multiple projects in Metrix. And I will show you the results of another project, just so I can show you what our coverage browser looks like. So basically you can navigate through your coverage hierarchy and if you're familiar with functional coverage, you'll know you can get down to the bins area, and we've got a filtering capability built in here. So if you would only like to see the bins which are not covered, you can add filters for that, and you can see that allows you to focus on the most interesting results the coverage holds. We also have links to source code to help you identify if your coverage code was perhaps the problem here, and the links that we provide are always to the particular version that was used in this particular regression. So let me go back to SweRV. And I didn't go over this, but we have a dashboard page that gives you an overview of how your project is changing over time in terms of test pass rate and coverage metrics. So I'll go quickly back to results. I'm very conscious of the time we have here, so let me show you some detailed test results. So these are the tests that are part of the GitHub repo, and with each of these, we can view a log file. So I'm going to go to Hello World because this is a bit of an echo of Michael's demo. And here you can see the log file for running the Hello World test. You can see Hello World from SweRV EH2. We also have a waveform viewer that is running in the cloud in our browser. So this is the first browser-based waveform viewer in existence. And when it opens, the user interface should be familiar to people who are used to debugging RTL and using waveform viewers. You can either navigate the hierarchy and choose to add signals manually, or you can load a saved session. So I'm going to load this one that I prepared before this demo, just to show you what it looks like. And what I will do, I will scroll and show you that data is loaded on demand, which means the performance of this is very good, despite the fact that it's running in the cloud on a Google data center. And Metrics is constantly developing our waveform viewer, adding new features, and responding to feedback from our customers. Let me go back to our results. And so we have the ability to rank simulations according to their contribution to coverage. That's what you're seeing here. We have the ability to open multiple log files, to create coverage reports dynamically. And for any simulation, you can choose to download the artifacts associated with it. So any artifacts that your simulation creates, such as waveform files, log files, any arbitrary compile artifacts, you have the ability to download those as well. I should mention that Metrics uses Docker containers. We provide our software in a Docker image. We can add to that image any software that you require, open source, or anything that you own or licensed. And working with Codasip, we'll be able to provide the SweRV Support Package that way as well. So let me go back to results here. You can see our example is running, and there are 4 tests that are still in the running state. I think I'm going to leave it there.
So maybe while it's running, let me ask you a question that came in, Amy. Can you use the command line interface?
So we do have a command line interface to our simulator, and we do have the ability to launch simulations or regressions on Metrics from the command line. We have a REST API and an ability to authenticate from other applications. So if you were working from your own machine or from, say, a GitHub or GitLab pipeline or something, you have the ability to use us in that context.
Okay. Yeah. So maybe at the end, when you're done, there's a question in the Q&A box, and you can type an answer, or Dan can type an answer to the question. Thanks.
Let me also ask you another question while it's running. I didn't mention it, but the metric simulator will be included in the Codasip SSP. We'll have access to a cluster that's pre-built. It'll have all the SweRV cores in there. It'll have all the test benches. So literally, you'll be able just to go into the support package and access the metric simulator SweRV.
So Dan, is there a certain amount of time that's included with that, or?
Yeah, we're going to bundle up 1,000 free minutes for anybody who downloads the SweRV Core. So that the idea is, I'm from Missouri, so it's show me. So for me, it's I want to go in, modify a SweRV Core, use the Codasip tools, generate the update, and I want to simulate it and go, wow, that's the whole loop. I modified and I verified all within the cloud, all without paying for any big upfront. We have customers in startups that have 10, 15 engineers, and their costs are $700, $800, $900 a month. So I give you a comparison to what you'd pay for a commercial EDA simulator. And again, it's that massive parallelism that makes this all worthwhile. So there you go. I'll let Amy wrap up. I know we're running out of time.
Yeah, so you can see that the simulations that I started have finished. The results are going to be pretty similar to the others that we looked at. All these tests have passed. That's indicated with the green check mark. The logs are available. I didn't choose to dump waveforms for these, but you can see metrics, at least for assertions. So I didn't look at this, but we have an assertion coverage viewer as well, where you can take a look at the assertions in your design and get the statistics about their execution. Okay.
Well, I'm impressed that the live demo worked. Very good. Okay. So is there anything else you want to wrap up, either Dan or Amy?
That's all for me.
No, thank you for giving us the opportunity, and happy to answer any questions.
Yeah, so I thought I really wanted to thank all the panelists, everyone that had presented and shared the various presentations, and thanks Jeffro for helping coordinate this. So several of the presenters will be hanging out for a few minutes. If anyone wants to ask questions, you probably could unmute yourself if you wanted to really ask, or if you just want to type more questions, that's fine too, and we'll hang around for a few minutes and answer them. Thank you very much, again, everybody, for attending, and for the panelists and the presenters.
Thanks to CHIPS Alliance for hosting this and putting it all together. It's a great show. Thanks, Ted.
Welcome.
So it looks like Minden has a question. I'm going to.
Yeah, there's a couple of questions for either Dan or Amy.
Hello.
Hello.
Can you hear me?
Yes, we can hear you.
Hi, great. I try to find my unmute button.
Sorry.
So it's great to see that the open source has this all design flow tools and IPs available. I wonder, is there any kind of commercial company utilizing this flow and IPs to make a kind of commercial product?
Yes, certainly. In Western Digital, we are using both generations of SweRV cores for a variety of internal projects, targeting both commercial flash controllers, as well as other projects that are targeted towards more on the research side, the OmniExtend protocol development, and academic projects.
Okay,
then,
so the Western Digital.
And then there's several other companies that have not announced yet, but they're using SweRVs in their commercial offerings. And then
Okay.
And then Codasip has multiple confidential relationships of various people who are using SweRV Core.
I see. So the flow you are introducing today, is it kind of the recommended way of doing an open source project?
You mean the flow that Codasip has shown, or?
Yeah, and also the cloud EDA thing. Just yeah.
No, obviously with open source you have multiple options that could be possible and available to you. We sort of wanted the CHIPS Alliance to start, to pick some starting points and enable companies who are used to getting their work done with various EDA tools partners to sort of have some starting points. But I don't think it's the end. There's probably going to be a few more.
Okay. Just last question. So the EDA tool showing some verification capability. How about the kind of backend physical implementation? Does that provide that function as well?
Oh, yes, that's a great question. Yeah. So I think maybe somebody. Let me just add one quick answer, and then I think that you will get multiple answers to this question. We haven't tackled that yet. When you have a commercial design flow, every tool in the flow is adding IP, and added IP is obviously confidential, cannot be released. We are looking at that problem from long-term perspective, and we do have a project Open Road that's a fully open flow. They have joined the CHIPS Alliance, and they are also running weekly SweRV EH2 runs in a fully open flow. Now, that's more of an academic project, but it does have a lot of attention. It's very likely to have a 130 nanometer tape out very soon. So check the Open Road project. Yeah.
Okay.
And then I'm
Thanks.
sorry, somebody else on the panel wanted to answer, so I don't want to dominate the answers here. Please go ahead.
So this is Dan from Metrics, and one of the advantages of in the cloud is you avoid all those patents issues. You're actually just using the technology. You're not acquiring it, you're not installing it, you're not protecting it and securing it. And that's more and more one of the reasons why people are moving to the cloud. Our intention as a company is to have a full RTL to GDS2 flow in the cloud, with all points in between, logic synthesis, design for test, clock tree synthesis, static timing, place and route. Extremely important to startups who generally struggle, especially during the pandemic, to raise money. Being able just to pay as you go and without a big capital raise and send it off to the traditional EDA vendors. But we chose first to tackle verification because it's the biggest task in the flow. And that's why we came out with our System Verilog simulator. But you'll see over time that we'll be releasing more and more tools, eventually being a full RTL to GDS2 flow.
I see. Thank you, Dan.
You're welcome.
Okay, so there's another question, Dan, maybe you can take a look at that. I think it's probably most targeted to metrics.
Yeah.
And if there's any other attendees that want to ask a question.
So the question's about pricing, and pricing per cloud vendor varies slightly. So there's no one answer. In fact, many companies have their own private clouds. We can run on private cloud as well. The pricing per storage, per virtual machine, for execution, whether you're memory intensive or storage intensive, every vendor is different. For metrics, we package up those prices and deliver that to the customer so that they're only paying us per minute, and all of those prices are absorbed by us. So in the simplicity of this, it's a user wants to use a cloud simulation. He's essentially opening an account with us on whatever cloud vendor they choose, and we'll bill them per month or per quarter.
Great, thank you.
I have one more question for Dan. So the cloud-based EDA, is it fair to say that at the moment is mainly targeted at kind of a simpler design, like maybe MCU based, for a kind of full-blown complex, like for example, server chip SoC design? Would that be suitable to use a cloud EDA tool?
Oh, absolutely. In fact, our focus is on big, complex designs that can really benefit from massive parallelism. So actually, the bigger the design, the more impact we have, because again, we're exploiting parallelism. So if you have a 8-core, you've got 8 different SweRV cores in there, and you maybe have a little EL2 as a minion, and you've got a ton of IO, and you've got closely coupled memory. All of that, that's where our value comes in, because we can run that simulation and exploit 20,000, 30,000, 40,000 different cores all running in parallel. So that's actually if you think of Verilator as compared to metrics, we're targeting the big random tests, the big regression tests, the big SoCs. It's all about capacity, where you'd have to have lots of storage on your data center that maybe you don't want to pay for. And again, during this time when everybody's working at home, I doubt there was any CEO in the semiconductor industry who contemplated every one of my engineers will be dialing in and working from home. And that's where we're at in 3 months. The cloud makes that. There's no VPNs, there's no direct connection. It's all done in the cloud. And you can be anywhere at any time. You have access to it. And that's what's driving people to say, this just is simpler. It's an easier infrastructure. And people are just getting tired of having to babysit and update and patch all their hardware and software. So I kind of took a long answer to a short question. My apology. Yes, we will have VHDL in Q4 of this year.
Okay, thanks.
Can I boot Linux on EH2? I'll leave that to you, Zvonimir or Srini or Robert.
No, you can. Sorry, I haven't seen that question. Oh, can I boot Linux from EH2? No, you cannot. EH2 is an embedded core. It doesn't support modes you typically need to run fully featured operating system. It's actually targeting RTOSes. So
Right, there's no MMU in it. There's no MMU in the core.
Not just MMU. There's no user and privilege mode.
Okay.
So our next generation core will be a Linux application.
Which you don't want to say anything more about at this point.
Sure.
What core?
Right, exactly.
Buy me a beer.
Okay. Well, this is awesome. I mean, I'm super excited that we've had this level of interaction, number of attendees. So since we're having a good time, we'll hang around here for another minute or two. If there's any other questions that you attendees have, let's just, raise your hand, ask them live, or type them in the Q&A.
Yeah, it hasn't been clear to me if people are supposed to ask questions in the webinar chat or in the questions and answers. So we kind of try to monitor both. Problem with webinar chat questions is if a lot of people ask questions in the same minute, some questions just disappear at the top.
Yeah, there were a few in the chat that I was trying to catch up, but hopefully people got their answers. If not, they should post it in the Q&A.
So Ted, you're officially running the show.
Yeah, I mean, so all right, I'm going to call it an end then. I think we're done. I want to thank again everybody who participated, who attended. I saw some terrific comments, positive comments. So we tried to make this educational, informational, and also entertaining. And really look forward to newer events that we will be having. So. The Bay Area group will be doing another event in just a couple of weeks. I'll probably be posting something tomorrow, so you can keep an eye out for that. Thank you guys very much, everybody, again, for attending and for presenting.
See everybody.
Thank you.
Okay, bye-bye.
Good, thank you, bye-bye.
Thanks, Jeffro.
You bet.
Thank you, bye-bye.
Bye-bye.
Bye.